Hi everybody, this is our lesson on probability models from chapter 17. We start out, we've got to make sure we understand what Bernoulli trials are. We talked about these in class, and a Bernoulli trial is a random event that has two outcomes, has the probability of success that remains constant throughout the problem, and the trials are independent. We did look at what happens when that's violated, that we might be able to overlook that, the exceptions to that rule, but we're going to continue for now, saying where we've got independent. If we look at the geometric model is when x is a geometric random variable. And first, if we have a geometric model, we need to have the conditions for a Bernoulli trial. So first, we need to consider, of course, is something split up into success versus failure? And then we need to know, is the probability a constant? And then do we have independence? We're going to check that each and every time. But the piece that makes this a geometric model is the fact that the trials, the random variable itself is the number of trials it takes to achieve the first success. So to calculate the probability for this, we have a formula, and the formula is q to the n minus 1 times p, which is the probability of success. Q, of course, being the probability of failure. And n is the number of trials that it takes to get there. To find the mean over time, or the average over time, we're going to just take 1 divided by the probability, and our standard deviation is going to be the square root of q divided by p squared, that whole quantity divided by the square root. Okay, so let's look at an example. If we have a basketball player who makes 80% of his foul shots, and we assume independence, we're going to try to find the probability that he makes his first basket on his fifth shot, and we're going to find the probability that his first basket occurs on one of his first 3 shots. So let's, of course, make sure we have a random variable. And do we have success versus failure? And we do. Check. Do we have, in this case, the probability of success is going to be constant? Yep, it tells us it's 0.8. And finally, it tells us right here to assume independence. So finally, we just need to check the last thing, and we need to know, is x the number of trials until the first success? And in our examples, that's exactly what we have. First success. I got carried away. Okay, moving on. Now, if we look at our example again, we know that p is equal to 0.8. And in this example, we're saying that n is going to be 5. So we're going to say 0.2 to the 4th, which is n minus 1, times 0.8. That will give us the probability that it will take 5 baskets for him to get his first shot, for him to make his first shot and actually have it be successful. And that probability is 0.00128. And again, 28. And again, we're normally going to round to the 4th decimal place, but for right now, I just want to make sure you can see where these numbers are coming from. And our second question is, what is the probability that his first, the shot that he makes first will be either the first one, the second one, or the third one? So we have to find the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3. So we're going to apply this formula 3 different times. We'll have 0.8, which is a success on the first shot, 0.2 times 0.8, which is the probability of his first success on the second shot that he takes, and 0.2, whoops, 0.2 to the fourth, to the second times 0.8, which is, of course, when he makes it on that third shot. And when we put all of that together, we get 0.992. Okay. We also could have a binomial random variable, and first thing we need to check is that it's a Bernoulli trial, and the second thing we need to check is that X is actually defined as the number of successes in a set number of trials N. So we're going to look for the probability that X is equal to K, where K is the number of successes out of N trials. Okay? And so the formula here is very complicated because we have to consider all the different combinations. And that's going to be N factorial over K factorial times N minus K factorial times P to the K power times Q to the N minus K power. Now, this part right here, let's switch colors for a sec. This part right here describes a single result where you have exactly K successes. But we need this value, which is over here. This is called the binomial coefficient. Binomial coefficient. I'm going to abbreviate. And it's called the binomial coefficient because what it does is it tells you how many different ways there are to list out all the different ways that you can get K successes out of N trials. It's a little tricky. We're going to look at a couple examples in a moment. The other formulas that we need are the formulas for mean, which is very easy for this one. Oops, let me go back to the blue. And this is just NP, and the standard deviation is the square root of NPQ. Okay, so let's take a look at an example. A basketball player makes 80% of his foul shots. He typically takes 6 foul shots in a game. Assuming independence, first we're going to decide if we have a binomial random variable. Is this an example of Bernoulli trials? Yes, it is, because we've already checked that, because when we checked the question that was geared towards a geometric model, we knew that. And the only other thing we now need to check to see if we have a binomial random variable is if X is the number of successes out of a set number of N trials. And so in this example, we have X is equal to the number of foul shots made in 6 attempts. And so yes, we have a binomial model here. If we continue with the example, let's consider the following probabilities. Same scenario, but now in a game, our player makes exactly 5 shots out of the 6 shots he takes. Or, for the second example, in a game he makes at least 5 shots, of course, out of the 6 that he takes. So let's take a look at this. This is going to be a little bit more complicated. So if he typically takes 6 foul shots in a game,